We are now going to see how quantum processes and holons have a mathematical basis, and how they can account for many puzzling scientific phenomena. Originally scheduled to be on one video, it has become apparent that this is better set out as 4 videos. So this is video 12A. Videos 12B, the stability of matter, 12C, uniting the forces of nature, and 12D, making sense of the double slit experiments, follow. In previous parts of this series, we've investigated how quantum processes and holons work together to explain the physical universe and how we are conscious of it. We discovered that reality and consciousness are completely inseparable. We worked our way through explanations for a wide range of phenomena. We accounted for space, structure and form, materials, solids, liquids and gases, life and consciousness, why we make tools, cyborgs, how we think, what our minds are and how we make up our mind, why we have families, societies, corporations and countries, where our emotions come from, how we can be of balanced or unbalanced mind, groupthink, spirit and spirit communication, cosmic consciousness, absolute sentient power, spirituality and religion. Now, although quantum processes and holons have explained all these things, we need to show that this different way of thinking is scientific, and that it has a mathematical basis. It would also be good if we could provide some solutions for some puzzling scientific mysteries. In this video, we will look closely at some of Michael Faraday's famous experiments, and delve into the nature of electricity from a quantum process and holon point of view. We will come to a surprisingly simple explanation for why the Earth has a magnetic field, and why on occasions it reverses polarity. Let's start off by explaining in holon terms the commonly experienced nature of electricity. In part 3, Atoms and Light, we looked at how atom holons can be built from countless numbers of quantum reflexive processes that consist of pairs of oscillating quantum electrons. This is an illustration of a simple spherical holon. It can be any sized holon from an atom holon upwards. However, we will work with an atom-sized holon. Here are some quantum reflexive processes that form the outer shell of an atom holon. The boundary of the atom holon is made up of vast numbers of these quantum boundaries. The boundaries are electrical in nature. The charges that form the boundaries are confined within the atom holon by randomly orientated charges on the outside. So an atom holon is a structured electrical plasma within a larger plasma field. Atom holons are different from atoms in a particle and space view of reality. In a particle and space worldview, atoms are seen as electrons confined within their boundaries by a central positive charge in the atomic nucleus. This structure leads to all sorts of mysteries and complications. Why, for instance, don't the negative and positive charges just cancel each other out? As they don't cancel themselves out, how do they just happen to balance each other? And, as the nucleus of the atom is so very tiny and contains all the concentrated positive charge, how come the very strong repulsive electric force doesn't just blow the nucleus apart? The history of particle and space science investigations can be seen as an attempt to resolve these problems, and it has apparently been successful in doing so. We are familiar with electron orbitals and the protons and the neutrons of the nucleus. We are now conversant with families of fundamental particles called quarks, leptons and bosons. There are some 16 or so particles in these families that are related to the strong and weak nuclear forces that hold the nuclei of atoms together. This edifice of numerous fundamental particles is incredibly complex and convoluted. Fairly recently, it has been explained that fundamental particles can be accounted for by the presence of another more fundamental particle, called the Higgs boson. But already there is evidence that the Higgs boson might not be fundamental. It seems that given enough energy to smash particles together, we will always find smaller and smaller fundamental particles. Even the nuclear forces are problematic. For instance, the strong attractive nuclear force that holds protons together in the nucleus has this amazing and unexplained property of becoming a repulsive force just as the protons come very close together. This is not a good look for science. So, can the quantum process and Holons idea resolve these complex and convoluted discrepancies? We first need to explain the positive and negative electricity that we experience in the real world in terms of quantum processes and Holons. Here at the top of the diagram we are looking at two neutral Holons. They can be any size you like, but they are all made from countless quantum processes that consist of oscillating pairs of quantum electrons. The blue surroundings represent the outer shell of the Holons. Underneath, we see charge being transferred from one Holon to another. This leaves the donating neutral Holon with what we term a net positive charge, and the receiving Holon we term as having a net negative charge. Now, this way of looking at electrical charges is not new by any means. The idea that electricity is a single phenomenon, that is never created or destroyed, but merely transferred from one place to another, was discovered by Benjamin Franklin. It is called the principle of conservation of electric charge. So how do quantum process and Holon ideas explain some of the most fundamental experiments concerning electricity? Let's have a look at some experiments carried out by the great pioneering scientist Michael Faraday. In the early 19th century, Michael Faraday made many scientific advances, from discovering benzene to discovering the laws of electromagnetic induction. He was also the first to propose the existence of electric and magnetic fields. His ice pail experiment is one of his most famous. It is explained using two types of electrical charge. Let's have a look at it in some detail. Figure A shows a metal ice bucket with a lid, completely insulated from Earth. The bucket is connected to a gold leaf electroscope, whose leaves open only when the electroscope or any objects near it are charged. In this case, there is no charge nearby, so the electroscope reads 0. Figure B shows the situation when a negatively charged metal object is suspended inside the pail, but not touching it. The negative charge on the outside of the ball attracts the positive charges to the inside surface of the pail, while leaving negative charges on the outside surface of the pail. The electroscope registers the negative charge on the outside of the pail. Figure C shows the situation when the metal pail is then connected to Earth. The negative charges on the outside of the pail and on the gold leaf flow away to Earth, leaving just the negative charges on the outside of the object and the positive charges on the inside of the pail. The electroscope reads 0. Figure D shows the pail re-isolated from Earth, and with the negatively charged object removed from inside the pail. The positive charges on the inside of the pail move to the outside surface of the pail, and the electroscope registers those positive charges on the outside. This is known as charging by induction. This experiment is consistent with the particle and space view of positive and negative charges, and it is also consistent with positively and negatively charged holons. Now figure E shows that if the pail is re-earthed from the outside, then the positive charges run to earth and the gold leaf electroscope reads 0. The next figure F shows that if an attempt is made to discharge the remaining positive charges to earth by touching the inside of the pail, nothing happens. It is impossible to remove any charges from the inside of the pail, and it doesn't matter whether these charges are positive or negative. Now, the plausible and accepted explanation for these observations is that conductors can only have free charges on their outer surface, and this interpretation has great practical applications. Faraday cages shield sensitive electronics from stray electromagnetic fields. They also explain why, if we are in a car that is struck by lightning, we do not get electrocuted. The charges of the lightning bolt run to ground over the outside of the car, leaving the passengers safe in the inside compartments. Now, this explanation that excess charges on bodies reside only on their outer surface, although very useful, comes with some glaring logical and practical inconsistencies. Let's have a look at a cross-section through a charged sphere. On the left is a conducting sphere, and on its surface are some individual charges. On the right, we increase the charge on the sphere by adding another charge. The question is, where does this charge go? According to conventional thinking, it should go to position 1 on the outside of the sphere. OK, the surface charges shuffle about a bit, but the new charge is quite close to its neighbouring charges. The question is, why, as light charges repel, does it not go to, say, position 2, somewhere inside the sphere, where it is much further away from the other charges? It's like when you go to a crowded beach. You don't want to be close to other people, and they don't want to be close to you. Does this mean everyone crowds around the outside boundaries of the beach? Obviously not. People spread themselves out over the whole area of the beach, making as much room for themselves as they can, while sharing with others. And this is what these charges should do. They should spread out over the whole of the inside of the sphere. This simple logic is, however, denied by the assertion that charges can only be found on the outside of charged bodies. What is going on? Is there any evidence that free charges can be found inside a conductor? Well, here is another diagram. This time we are looking at a cross-section through a conducting wire that is going in and out of the screen. If an electrical potential difference is applied to the wire, then a current will be established in or out of the screen. In case 1, where the charges are on the outside of the sphere, there is no resistance to the flow of a charge. They can scoot along the surface. In this scenario, the conductor should be a superconductor. In fact, all conductors should be superconductors, but this is certainly not the case. In scenario 2, charges are presumed to be somewhere inside the conductor. It is obvious that they have to move through the body of the conductor. How fast they move will depend upon the resistance of the conducting body. This scenario ties in with Ohm's law of resistance in simple electronic current theory. So now we have a dilemma. How come Ohm's law works, but the charges are believed to be on the outside of conductors? Can a process and HOLON view of reality resolve this dilemma? Figure A at the top of this diagram shows a very simple linear conductor. It is one quantum process wide and a length L. Its boundaries are marked in red. Figure B shows a few of the quantum process charges highly magnified. But although we have shown them equally spaced along the conductor, we do not really know where we should place them. So how do we find out? Well, we know the quantum charges only exist in pairs. So figure D shows the first quantum pair that contributes to the existence of the conductor. We put these as near as possible to the centre of the conductor. Now, because the charges repel each other, these two quantum process charges move apart. They do so until they reach the boundary of the conductor. They reflect from those boundaries and move towards each other. When they reach their original positions, they repeat the process, so they oscillate to the left and right along the conductor. So we can now, figure F, put in the second pair of quantum electrons. These go on either side of the original pair. This arrangement observes a general quantum exclusion principle, such that quantum charges cannot occupy the same coordinates. This second pair of electrons also oscillates between themselves and the conductor boundaries. Subsequent pairs of quantum electrons can be added in the same way until a huge number, say n, are added. All these quantum pairs contribute to the existence of the conductor by oscillating between themselves and the conductor's boundaries. Now, as these quantum charges are all on the move, we can again ask the question, figure I, where are these charges at any particular time? Is there a quasi-steady state reached that enables us to know the charge distribution along the conductor? We need to do some calculations. In this slide representing a 20-meter linear conductor, we have a blue line along the bottom with its boundaries marked in red. And shown above the line so that we can see them, we have 2,000 quantum process charges. Each pair are equidistant from the centre of the conductor. We can drop these charges onto the line to imagine their position along it. We now take each pair of quantum charges to be quantum electrons. This gives them quantum mass, and we can calculate where they all end up at some random quantum time in their individual oscillations. When we do this, the quantum charges fall into a quasi-steady state. They arrange themselves throughout the conductor, with most of the charges being nearer the boundaries of the conductor and far fewer nearer the centre. This is very much an arrangement that we might intuitively expect. They don't want to crowd together near the centre, nor do they want to crowd around the outside perimeter. In the light of this new knowledge, let's build ourselves a linear conductor. For the sake of argument, we'll make it from lithium. Figure A represents the arrangement of quantum process charges that we have just calculated. The darker blue represents a higher charge density and the lighter blue a lower charge density. Figure B represents a line of lithium atom holons, highly magnified. Figure C shows the same arrangement of charge density that we calculated for the linear holon. But in this case, we are applying this arrangement to the conducting band charges of the lithium holon. That is, to the charges that are free to move between the conductor's boundaries. Figure D illustrates the completed linear lithium conductor by combining figures B and C. There is a core of lithium atom holons consisting of their individual bound quantum charges and delocalized conducting band charges that are free to move. We can now illustrate a three-dimensional lithium conductor holon. We will just concentrate on the conducting band charges. On the left-hand side, we are illustrating how we can add together the linear holons to form the spherical lithium holon on the right. Of course, on the paper, we can only illustrate a cross-section through this sphere. Nevertheless, the idea is pretty straightforward. So always remembering that this sphere is also made up of lithium atom holons, we see the arrangement of the delocalized conduction charges. These are spread throughout the sphere, but with a greater concentration of charge towards the outside. So how does this help us solve the initial problem of where do excess quantum charges go in conductors? Inadvertently, we've already calculated where they go. Here we have exactly the same diagram as the previous one. Excess free charges on the sphere have exactly the same charge density profile as the conductor's delocalized conducting charges. This is simply because when we are looking at the conducting quantum charges, we were looking at free charges within the conductor holon. If we add some more free charges, if you like overcharging the holon, those charges follow exactly the same dynamic rules as the delocalized conduction charges. Hence, excess charges on conductors have a charge density arrangement that we see in the diagram. That is, the charges are dispersed throughout the conductor. The greatest concentration is near the outside, and there is less of a concentration towards the center. Ultimately, there is zero concentration in the center, because any charges in this position would experience an infinite electrostatic force pushing them apart. More of this later. We should also note that if there is a deficit of charge within the conductor, then more of the charge deficit appears near the surface of the conductor and less towards the center. This is equivalent to saying most positive charges on a conductor are to be found near the surface. What in the particle and space paradigm are called positive holes behave the same way as negative charges. We see that the quantum process and Holon paradigm solves the particle and space paradox of light charges crowding together on the surface, even when there is room on a conductor for them to move apart. A dynamic quantum process approach allows for the excess charges to distribute themselves throughout the conductor. So what about other puzzling aspects of conductors? Why can you take charges off the outside of conductors, but not off the inside? Here we have a similar diagram to the previous one, but this time we have taken the core out of the center of the sphere. The dark blue line represents a linear section through this hollow sphere. So here diagram A represents the line cross-section that we looked at in the previous diagram. B to F show that we have the same dynamics for the hollow sphere as for the solid sphere. All quantum process charges move away from the inside boundary of the sphere because of their mutual repulsion. They eventually reach the outside boundary of the sphere, where they reflect back towards each other again. When they reach their original positions, they are halted by their mutual repulsion and again move away towards the outer boundary. We can now see why excess charges on conductors can be removed from the outer surface of the conductor, but not off the inner surface. All charges move towards the outer surface, so given an opportunity to move further away onto another conductor, they will do so. In contrast, at the inner surface, charges are either stationary or moving away from that surface, so they cannot escape from the inner surface. In the quantum process and HOLON view of Faraday's charge pail experiments, quantum dynamics explain why charges cannot be collected from inside surfaces of conductors. Faraday cages work not because charges are on the outside of the cage, but because none of the charges can get off the inside of the cage. Quantum process and HOLON interpretation of these experiments has far-reaching consequences. So, for instance, the distribution of excess quantum charges on spheres applies to all sizes of conducting spheres. So as the Earth is a conducting body, a charged Earth will have a large element of this internal charge distribution. The Earth is made up of vast numbers of matter holons with complex dynamics, so excess charge distributions would be more complex than in a simple sphere. However, charges inside a rotating Earth and quasi-stationary charges in surrounding space can provide a source of electrical currents to generate the main components of the Earth's magnetic field. Other magnetic components of the field can be explained by other internal charge movements. In this scenario, magnetic reversals of the Earth's magnetic field are explained simply as being due to the net charge on the Earth cycling from negative to positive and vice versa. The changes will take place as positively or negatively charged holons arrive at the Earth from cosmic space or from the solar wind. The observed fact that magnetic reversals coincide with periods of a weak terrestrial magnetic field are entirely in keeping with this scenario. In part 3, Atoms and Light, we looked at how the Sun HOLON can be considered to be made of trapped light. Strictly, vast numbers of electromagnetic quantum processes. It is a short step to propose that the complex cyclical magnetic properties of the Sun are driven by charge excesses and charge deficit cycles. The quantum process and HOLON paradigm opens up routes for interpreting many other astronomical and cosmological phenomena. Can quantum processes and holons throw light on any more scientific problems? In the next video, 12b of the series, we are going to have a look at the stability of matter, why some elements are stable and others are not. We'll also find a clue to explain why the universe is apparently expanding.